Okay, welcome back. So today we're going to be finishing up section 10.8, and then we're going to be moving on to 10.9. So let's kind of just do a quick review of what we talked about at the end of yesterday's lecture. We implemented or kind of talked about the concept of these normal and binormal vectors. So we had the normal vector, which was defined as the derivative of the unit tangent vector over the magnitude of the derivative of the unit tangent vector. Right, so this is just kind of how the unit tangent is changing with respect to time, and we renormalize it so that it's another unit vector. And then we go ahead and we also define the binormal vector, which we denote by a capital B. And this is the tangent unit vector crossed with the normal vector. So this T and N and B vectors kind of gave us this framework, which we called this T and B frame, right? And that was kind of moving this Cartesian coordinate system to a moving entity, right? It's how we live our life. We live in this T and B frame where everything else kind of looks like it's moving around us as we kind of transition through space. Okay, so let's do an example. Just kind of warm up those math ideas. So we're going to find the normal and binormal vectors for the helix. So we're going back to the helix here, doing some more calculations. Last time, I believe we looked at the curvature of the helix. So we're doing A cosine T, A sine T, and B T. Okay, so in order to find the normal vector, we're going to need to find the unit tangent vector. We have a question. What's the equation to find the unit tangent vector? Well, we're going to do it right now. So the unit tangent vector, if we remember, is r prime of t over the magnitude of r prime of t. So we're going to need this r prime. Well, r prime of t, we go ahead and differentiate our helix expression, our parameterization for the helix. We get negative a sine of t. We get a cosine of t and b. So we also need the magnitude of this vector to form the unit tangent vector. So let's go ahead and calculate that. We have the magnitude of r prime. Well, this is the square root of a squared sine squared of t. And then I'll have an a squared cosine squared of t. And then my last term here gives me a b squared. It's all under a square root. So because our sine squared and cosine squared have the same coefficient here, we can group them together and we'll just have the square root of a squared plus b squared. Okay, so that means that our unit tangent vector is this 1 over the square root of a squared plus b squared times our vector r prime, which was negative a sine of t, a cosine t, and b. Let's just kind of write that. Let's bring this coefficient into our vector. So we have negative a over the square root of a squared plus b squared sine of t. Then we have a over the square root of a squared plus b squared cosine of t. And then b over our square root of a squared plus b squared. Okay, so that is our unit tangent vector. So now to find the normal, so let's go back up here to our definition. The normal was the derivative of the unit tangent divided by the magnitude of that derivative. Okay. So let's go ahead and look at the derivative. So we have the unit tangent prime of t. Here we'll get a negative a over the square root of a squared plus b squared cosine of t. Here we'll get a negative a over the square root of a squared plus b squared sine of t. And here, this is still constant with respect to t. So this term is just 0 here. Okay, so now we need the magnitude of this vector. So here we have the magnitude of t prime. So I'll have an a squared over an a squared plus b squared cosine squared of t. I'll have another a squared over a squared plus b squared, this time times the sine squared of t. And then I have this plus 0 term. So I'm just going to end my radical here. So once again, we have the same coefficient out in front of our cosine squared and sine squared. So we can go ahead and write that as a over the square root of a squared plus b squared. So we divide this quantity to get our normal vector. Let's get rid of that little dot. So this is t prime of t over the magnitude. So here's our vector. And if we divide through by this a over a squared plus b squared, it's really nice because we're basically multiplying by the reciprocal of this, right? And notice that the terms out here are going to end up canceling. So let's actually just kind of write this intermediate step. We're dividing by this magnitude, which is multiplying by the reciprocal. So we have a squared plus b squared over a times our vector negative a over the square root of a squared plus b squared cosine t negative a over the square root of a squared plus b squared sine of t and 0. So if I bring out this coefficient into all my terms here, I just end up with negative cosine of t, negative sine of t, and 0. Pretty cool. We got rid of all those a's and b's. Okay, so now let's kind of scroll up back to the top to look at our definitions. We need to find this binormal vector, right? And this is the cross product between the tangent vector and the normal vector. So let's go ahead. So our b of t is defined as our unit tangent vector crossed with our unit normal vector. So let's go ahead and set up our determinant. We have I hat. And then in our x component for t, we had negative a over the square root of a squared plus b squared times sine of t. And then the x component for our n vector was just negative cosine of t. Then we have our j hat. So here we had a over the square root of a squared plus b squared cosine of t. And we had negative sine of t here in the lower. And then finally, we had our k hat. Here we had b over the square root of a squared plus b squared, and then we had 0 here for n. So that's our determinant. So let's set this up. This is equal to, so let's look at our x component. Our x component will be the determinant of this block right here. So we have 0 times this quantity, so we don't even really care what this is, 0 times that. And then we're subtracting our b over square root of a squared plus b squared times our negative sine squared. And remember, we're subtracting that quantity. So we'll get a b over the square root of a squared plus b squared sine of t. Okay, so for a j, and remember we have to think about adding an extra negative at the end for j. We're looking at the determinant of this column with this column. So we have 0 again times this upper left corner. Well, that's just going to give us 0. And then we're subtracting this b over the square root of a squared plus b squared times this negative cosine. And so remember, we're subtracting this multiplication, but there's also that extra negative from this j hat. So here we have negative b over the square root of a squared plus b squared cosine, oh, let's put parentheses there, of t. And then finally, in the z component, we're looking at the determinant of this little block here. So we don't have a 0 this time, but actually it's not too bad. So what we're going to think about is, let's look at this first term here. I have a negative sine of t times a negative a over the square root of a squared plus b squared sine. So from this multiplication, I get a positive a over the square root of a squared plus b squared sine squared, right? Over here, I'm subtracting the multiplication of these two entities. So I have a over the square root of a squared plus b squared times cosine t multiplied by negative cosine of t. So it looks like I have this double negative. I have this negative here, and I'm subtracting this. So I have plus the a over square root of a squared plus b squared cosine squared. So it looks like I have the same coefficient again, and I have a sine squared plus a cosine squared. So this last term ends up giving me and a over the square root of a squared plus b squared. And that's our binormal vector. So kind of think about what these represent, right? If I have the helix defined by my a cosine of t, my a sine of t, and my bt, you have this circle that's kind of unraveling. It has a radius of a, and it's moving up at a rate of b. And wherever I am at a given time t, I can construct a new coordinate system from this t, n, and b framework. So let's kind of talk about this t and b framework a little bit more. So we know that they're all orthogonal to one another. So imagine we are at some given point here. The way that we're traveling is going to define our t vector. We're also going to have a normal vector that depends on how t is changing with respect to time, and it's orthogonal to it. And then from both of these, we are generating a third orthogonal vector that is the binormal. So here we have t, here we have n, and here we have b, our binormal. So now realize that this is kind of like a Cartesian coordinate system, and they have planes, right? Instead of saying like the xy plane or the xz plane, we have names for each of these planes in the t and b coordinate system. So can I do a dotted line? A dotted line would be great here. No, I can't do a dotted line. Okay. A solid line is probably okay. So let's look at these planes that we kind of generate. So we have 3 different planes here. The plane that shares t and n, this is the osculating plane. The plane that t and b share, this is the rectifying plane. And the plane that n and b share is the normal plane. So some questions that you could see on homeworks, quizzes, exams, yada, yada, might be you have some kind of particle that's moving. Can you find the rectifying plane at this specific location? Can you find the osculating plane here? So to do that, to find those planes, note which vector is orthogonal to the plane, right? So if I ask you to find the normal plane, the vector that's normal to the normal plane is t, right? If I want you to find the rectifying plane, the vector that's normal to this plane is the normal vector. If I ask you to find the osculating plane, the plane or the vector that's orthogonal to this plane is the binormal vector. So let's look at our above example here. If I wanted to find the osculating plane, right, I needed this binormal vector. That's my normal vector to this plane. This, oh, I didn't even put an end on that vector right there. Let's do that. There we go. This would be the coefficients that I put in front of my x, y, and z terms. Just like how we found a normal plane, right? A normal plane equation where we had some ax plus by plus cz is equal to d. This would give me those coefficients out in front, right? And if I plugged in a given time that corresponds to the point that I'm currently located at, this point here, then I can find this osculating plane, right? It's just like finding a plane that we've done earlier in this chapter, but now you just have to find the right corresponding normal vector to it. Okay, and with that, we conclude section 10.8. So we're gonna jump into the last section of chapter 10 here. So why don't we go ahead and start a new page. This is 10.9. Motion in space. This is a fun section. So let's kind of dive in here. If we consider some vector r of t to denote the position of a particle at time t, the velocity is defined as the limit as delta t goes to 0 of how the position changes with some small increment delta t minus r of t all over our delta t. And we know this to be the derivative r prime. Right, and when this is just officially announcing that, hey, look, we take this derivative here, we're gonna get this velocity. And we've also kind of defined this, but let's kind of put it in writing. So, however, the speed of the particle is the magnitude of velocity. Or the magnitude of this r prime. Now, the acceleration is then defined as the derivative of the velocity, or the second derivative of our position. Okay, so let's start off by doing a nice little easy example. Where we're going to find the velocity and acceleration of the particle with position cosine of t squared e to the 3t. Okay, so our velocity is simply the derivative of our position vector. So we go ahead and take the derivative here. We get a negative sine of t, a 2t, and a 3 e to the 3t. Our acceleration is our derivative of velocity. So we go ahead and take another derivative. We'll get a negative cosine of t, a 2, and a 9 e to the 3t. So easy enough, not too bad. So now we can also define position and velocity alternatively and define the velocity as the velocity at some time t naught plus the integral from t naught to some given time t of the acceleration u du. Right, and more or less this is just how much change of acceleration have we accumulated here, and then we're tacking it on to the velocity at some given point, and then we've got this velocity here. So we're basically integrating acceleration to give us the velocity, right? Velocity is the antiderivative of our acceleration. And we can do the same thing for our position here. So r of t is our position at some given point t naught plus the integral from t naught to t of velocity u du. And we're just, u here is just a dummy variable, right? We can't put t again because we're using t in this anagram. Okay. Question about, would I tell us if you had to use one or the other? I wouldn't necessarily tell you that you had to use one over the other, but let's do an example where I think it's kind of clear that we have to do it this way. So we're going to find velocity and position when r at time 0 is the vector 0, 1, 0. Our velocity at time 0 is 0, 1, 1. And our acceleration at a given time t is the vector 2, 4t, negative t. Okay. So to find our velocity, this is our velocity at some t naught, which they've given us as 0. So this is the vector 0, 1, 1, plus the integral from 0 to our given t of the vector 2, 4t. Oh, sorry, we're using u here. So we're doing 4u, negative u, du. So 0, 1, 1 plus, so we integrate, so we get a 2t, and this is after we plug in our bounds as well, and then we get a 2t squared and a negative t squared over 2. So we end up with 2t, 2t squared plus 1, and a negative t squared over 2 plus 1. Okay, now that we have velocity, we can work on position. So position, our r of t, is going to be at our starting location, which is given by our r naught here, which we said was 0, 1, 0. And now we're integrating from 0 to t of our velocity vector with units. We have 2u squared plus 1, negative u squared over 2 plus 1 du. Okay, so we can integrate that and plug in our bounds. So here we have 0, 1, 0. And after integrating and evaluating at 0 and t, we end up with a t squared, a 2/3 t cubed plus t, a negative t cubed over 6 plus t. So we tack on that additional vector, And our end result is a t squared 2/3 t cubed plus t plus 1 and a negative t cubed over 6 plus t. So I hope that answered your question. I don't necessarily need to tell you which method to use. It can kind of be conveyed through how we're kind of framing the question, right? In our first example, we were given position and we were asked to find velocity and acceleration. So the only way to do that is to differentiate. But here, I gave you specific position and velocity at a given time, not the general vector, but I gave you a general vector for the acceleration. So we can integrate to get velocity and position. Okay, so before we do our next example, it's a little bit of a doozy. Let's take our 5-minute break now. So let's get some water, let's use the restroom, and then we can come back and reconvene and we'll do this next example. Okay, so I think this next example merits its own page. It's a little bit of a word problem. So let's write down our little prompt. A projectile is fired from the origin at an initial velocity v naught at an angle of elevation elevation of alpha, which is 45 degrees. A target is set up at the point x subscript t for target, yt, and 0. Our goal is to find the velocity needed to hit the target. So we're trying to find this v naught. Given gravity is negative g k hat. And we're going to ignore air resistance, all that good stuff. Okay. So let's do kind of a rough sketch here, what's going on. Actually, we can kind of draw this in do it in R3 first. So at the origin, we're shooting this projectile at a 45-degree angle, and there's some target that's set up. And we're trying to find the velocity that allows us to hit our target. So here we have our X, Y, and Z axis. What I'm going to do is kind of try to simplify this problem by drawing the XY plane together. So I'll say that this is the XY plane. It's kind of like we're looking at this from the side. And this is Z. And then try to do a 45-degree angle here, like that. And then our projectile comes up and is going to hit some target location. So this is xt, yt, 0. So that's also our point over here, xt, yt, 0. And we have a 45-degree angle. And we have some initial velocity that we'll call v naught. This is at 45 degrees. Okay, so let's find this v naught for this general xt, y of t. So let's start with some Newtonian formatting here. So we have that the force is equal to the mass times our acceleration, which is our negative m g k hat. Okay, so this means that our acceleration is the vector 0, 0, negative g. And that makes sense, right? The only force that this projectile is feeling is just the pull of gravity, right? So we just have this negative g here. From there, we can start figuring out what velocity is. So velocity at any given time t is my starting velocity, the thing that I want to find, this v naught. And then I have to tack on this integral from 0 to t of a of u du, which is our v naught plus the integral from 0 to t of 0, 0, negative g du. Or in other words, this is v naught plus 0, 0, negative g times t. Okay, since I don't know what v naught is, and this is the thing that I'm trying to find, I'm going to decompose. So it's off here on the side. Let's decompose and say that v naught is the vector vx, vy, vz. Because I'm going to try to manipulate it with these components here. Okay, so that means that we can write this as the single vector vx, vy, and vz minus g times t. So if I find vx, vy, vz all together, I'm done. Well, Vz is basically, this is just so this is our decomposition, right, of V naught in the k hat direction. Basically, it means the z component of V naught, right? But what we can do is use our definition. This is k hat dotted with V naught over the magnitude of k hat, which should be 1. Or, because we can use this dot product definition, this is the magnitude of V naught cosine of 45 degrees. And that just makes geometric sense if we look back at our kind of diagram here, right? The z component, Vz, is just how far this is in the z direction. Well, this is just going to be our cosine of 45 degrees. Can I explain this step here? Yeah, so this is more or less just a more complicated way of writing the z component, right? Because this is V naught, right? And how much of it is in the k hat direction, right? So this is our scalar projection here, if you recall. So here, because we're at 45 degrees, this is, why is it at 45 degrees? It's because that was our angle of elevation from our problem, alpha. So the square root of 2 over 2. V naught in magnitude. So now we have a way of writing Vz in terms of the magnitude of V naught. So now let's keep going and see if we can find our position. So our R vector is some initial location plus the integral from 0 to t of V of u du. Well, our initial position is the origin. We shot from the origin. So that's just going to be 0. So all we need to worry about is this integral. So this is the integral from 0 to t Vx Vy, and our Vz I'll sub in now, our square root of 2 over 2, the magnitude of V naught minus g times t, or sorry, g times u du. So here we have Vx times t, Vy times t, the square root of 2 over 2, magnitude of V naught times t, minus g over 2 t squared. Okay, so what we're going to try to do now is find the t value that when our particle or our projectile hits the ground, right? So we shoot it up at time equals 0. Let's try to find the t value that when it hits the ground again. So we're going to find the time when we land. So I know our position, our Vx t, Vy t, the square root of 2 over 2 times V naught in magnitude times t minus g over 2 t squared is equal to the position of our target when it lands. So xt, yt, and 0. Okay, so this tells me, if I look at the z components, that I know this term needs to be 0. So I know that the square root of 2 over 2 v naught t minus g over 2 t squared is equal to 0. Or in other words, t is either 0, which is when it's shot out of the cannon or whatever it's firing, or I can use the Pythagorean theorem. Sorry, the quadratic formula, other one. T is equal to 1 over g times our square root of 2 over 2 v naught in magnitude plus or minus our square root of 2 over 2 v naught. So if we choose the negative here, we obviously get 0, which is perfectly fine, right? If we sub in 0 here, that's when we shoot out of the cannon, right? So when it lands, must be the positive of this. So we're looking at the t when we land is the square root of 2 times the magnitude of v naught over g. Okay, so now also going back to this expression here, we can look at the x and y components as well. So we also know that Vx is equal to this x over t, or xt over t, and Vy is yt over t. Great. We also have this t term here. So actually, we can go ahead and write that. Actually, I'll wait. So it looks like we can write Vx, Vy, and Vz in terms of the magnitude of our initial velocity, right? So the definition of the initial velocity, or the magnitude of it, right? So the definition of this is the square root of each of its components squared. So it's Vx squared, which we'll write as xt over t squared plus yt over t squared. And then our z component we wrote as the square root of 2 over 2, the magnitude of v naught. So this is 1/2 the magnitude of v naught squared, like that. So this gives us a way to try to solve for this magnitude. So if I square both sides, and then I subtract over this, this 1/2, on the left-hand side, I get 1/2 magnitude of v naught is equal to 1 over t squared xt squared plus yt squared. Well, now we have what this x and our t value here is this radical 2 magnitude of v naught over g. So let's sub that in. This is g squared over 2 v naught squared xt squared plus yt squared. So what we can do is multiply over this v naught here. Oh, and this should be, sorry, this should be squared here. There we go. So we multiply over the magnitude of v naught. We can cancel these 1/2s. So we have v naught in magnitude to the 4th is g squared xt squared plus yt squared. So we go ahead and take a 4th root. So we can finally get the magnitude of v naught. This is the square root of g times the 4th root of our quantity xt squared plus yt squared. Okay, so now that we have our v naught in magnitude, so that's the speed that we have to shoot out of this cannon, well, we need our x, y, and z components. So if we backtrack through our process here, notice that we always have a way of writing our Vx or Vy or even our Vz up. Where was our Vz? There it is. Our Vz in terms of this magnitude, right? So all we do is just backtrack here. So Vx is this x over t, but t is the square root of 2 magnitude of v naught over g. Same thing with our Vy. So we can go ahead and plug all of those quantities back in, and we can find that our initial velocity in order to hit our target is the square root of 2g xt over the 4th root of xt squared plus yt squared our y component is the square root of 2g yt over the square root of xt squared, oh, sorry, the fourth root of xt squared yt squared. And then our square root of 2g over 2 times the fourth root, so this is in the numerator, our xt squared plus yt squared. Then end our vector. So you've probably done a problem like this, except you were in R2, and you didn't really have to think about a kind of like horizontal position in R3. But we've done it. We've used vectors, and we kind of figured out what the initial velocity is at a 45-degree angle to the ground. We shot this cannon, this projectile, and any arbitrary x and y location given by xt and yt will hit it, as long as we use this as our initial velocity. Now, how much gunpowder you need to put in the cannon to get that might be another calculation. And we didn't talk about air resistance at all, but yeah, it was a little bit lengthy of an example for sure, right? But not too bad. Okay, so I'll give you guys just a few moments to see if we've got any questions or you need to write down. I'll kind of scroll up a little bit in case you need to write down something. Would this be representative of the rigor of the exam problems? This certainly was a little bit longer than I'd imagine a part of the exam will be like. The questions will typically be formatted where you will be asked multiple things about the scenario, as opposed to this was finding one entity or one quantity in this word problem, where the other word problems I think will be a little bit more, can you find this or can you find that in these scenarios? So I think this was definitely longer than any component of those questions. So maybe not as hard as this. But if you can do this, then I think you're in good shape. But I wanted you guys to see it. When we calculated V naught in magnitude, how did we get that the z component was 1/2 of V naught squared? This component right here. So we said originally that Vz was the square root of 2 over 2 V naught. And if we square that, we get 1/2 magnitude of V naught squared. Just kind of scroll through, and then we can move on to the next part. Okay, so let's just start on a new page, because that was a lot of work there. Okay, so let's start talking about tangential and normal components of acceleration. All right, so before we kind of dive in, let's kind of remind ourselves what this tangential and normal component of accelerations are. So imagine you're driving, you're in a car, and you're coming up to a turn. You're going around this bend. Your car feels some acceleration. If you're stepping maybe harder on the pedal, you're trying to speed up or slow down around this bend. Your car will feel acceleration in the direction that it's currently headed. But as you'll note, as you start to turn, your body will kind of want to go a little bit horizontally in your seat, right? This is the normal component of acceleration, right? You're feeling this force that's kind of acting tangential, or sorry, perpendicular with the tangential component. So these together make the total acceleration vector. But let's see how we can kind of decompose these things. So before, we defined the unit tangent as our r prime over t and the magnitude of r prime over t. So now we can say, shouldn't be a derivative, that our unit tangent is simply our velocity over our speed. And another way to kind of decompose this here would just be to say that our velocity is equal to our speed in the direction that we're traveling in. Right, so we say that velocity is our speed in a certain direction, in the direction that we're traveling in. Right? Okay. But we know that acceleration is the derivative of our velocity. So we say that our acceleration is our derivative of velocity, which is the product rule on these terms here. So we take the derivative of the first, which is the derivative of the speed. So this is not acceleration. This is the derivative of the magnitude of velocity. And we'll get to that in a second. And then we have our tangent, our unit tangent. And then we have our speed multiplied by the derivative of our unit tangent. Okay, now curvature is coming back into the mix. So we recall that the curvature, this kappa of t, one way of writing this was the magnitude of t prime of t over our speed, so the magnitude of r prime. So we can rewrite this as the magnitude of the derivative of our unit tangent is our curvature times our speed. Now, we also note that our unit normal vector was defined as the derivative of our unit tangent divided by the magnitude of the derivative of our unit tangent. So by this, we can say that the derivative of the unit tangent is equal to the curvature times the speed squared in the normal direction. Thus, we can write our acceleration vector as the derivative of speed in the t direction plus the curvature of the speed squared in the n direction. Let's put t here. But I want you to kind of note, and I'm going to write it in such a way, I've got some thing out in front of this t vector, and then I've got another thing, which I'll call an, out in front of this normal vector. So what I've done is decompose the acceleration vector in terms of a tangential component and a normal component. So it looks like the thing that I've found out in front of t is my tangential acceleration, and the thing that I found in front of this n here, this is our normal component of acceleration. Right, so let's kind of define those. Where AT is the tangential acceleration, and AN is the normal or the centripetal acceleration. So it might be nice to express these terms in terms of our R of t, our parameterization, right? So let's note how we could do that. I guess before we kind of go on this journey, right, we have the tangential acceleration is the derivative of speed, and our an, our normal acceleration, is curvature times the speed, the speed squared here. So let's go and write that in terms of our parameterization. So in order to do that, we're first going to note that the velocity dotted with the acceleration is, so the terms for velocity is the speed traveling in the t direction, and it's dotted with how we wrote down the acceleration now is the speed's derivative. Instead of doing a prime, let's actually do the dt in the t direction plus curvature, the speed squared in the normal direction. Well, notice that these only share one common direction, this t, right? If I dot it, and this component's not going to show up at all because these are the ones in the same direction. So we'll get v and the times the derivative of the magnitude of v. So with that, we can say that AT, our tangential acceleration, is d dt of the speed, so the derivative of our speed, which is v dot a over the magnitude of v. Or we can write this as r prime of t dotted with r double prime of t all over the magnitude of r prime of t. So this is another way to find the tangential acceleration. You can find r prime, you can take its magnitude, you can take its derivative from there, or what we could do is find r prime, find r double prime, dot those together, and then divide by the magnitude of r prime. So these are two perfectly fine definitions for finding the tangential component of acceleration. So for an, this was the curvature of the speed squared. Well, remember the definition for curvature was the magnitude of r prime crossed with r double prime all over the magnitude of r prime cubed. And now we're just multiplying it by r prime squared. So finding an is not that much more difficult than going ahead and actually finding the curvature. Rather than having a cubed on the bottom, all we have is just power 1. So this is just the magnitude of velocity crossed with acceleration divided by speed, the magnitude of velocity. So this is just another way for us to find an. Okay, so we're going to do an example, and we're also going to find another way of calculating either of these. So let's form our example here. So without formally finding t and n, we're going to write the acceleration in the form AT in the unit tangent direction plus AN in the normal direction when the position vector is cosine of t plus t sine of t I hat plus sine of t minus t cosine of t j hat, where t is positive. Okay. So a lot of the definitions we've talked about involved the velocity. So let's go ahead and find the derivative here. So velocity is negative sine of t plus sine of t plus t cosine of t, and then cosine of t minus cosine of t plus t sine of t and 0. So it looks like our velocity vector is just t cosine of t and t sine of t and 0 in the z component. The speed just the magnitude of velocity is then t squared cosine squared t plus t squared sine squared of t, all in a square root. This is equal to the square root of t squared, which is equal to the absolute value of t. But since t is always positive, this is just equal to t. Right? That's why we threw in this little tidbit here, that t has to be positive. Okay, so now let's look at the derivative of our speed. So derivative of speed. This is just the derivative of t, which is just 1. So that already gives us that the tangential component of acceleration is equal to 1. Great. Okay, rather than going through and finding all of the curvature and r double prime and the cross product, all I'm looking for is an. So in general, if I have one of them, what I can do is, so let's kind of write this out. Now in general, the magnitude of acceleration squared by definition is a dot a. Right? Well, this in fact is equal to, if I plug in my definition for acceleration, this is a t in the t direction plus an in the n direction dotted with at in the t direction plus an in the n direction. Right? Okay, well, when I do this dot product out, I'll get at in the t direction dotted with at in the t direction plus at in the t direction dotted with an in the n direction plus an in the n direction dotted with at in the t direction, and then finally an in the n direction dotted with an in the n direction. So basically we're just foiling. But I look at all these dot products, right? This t dotted with n terms, we know that t and n are orthogonal to one another, right? So by definition, those dot products should be equal to 0. So we're left with at squared. And now I have the magnitude of t squared plus an squared, the magnitude of the vector n squared. But those are unit vectors. So we know their magnitudes, they're just 1. So I get at squared plus an squared. And that's just the Pythagorean theorem, really. Right? Our a is decomposed in terms of these orthogonal vectors. So the length of the hypotenuse is equal to each of those sides squared and summed together. So if I wanted to find an, or maybe I have an and I wanted to find at, something like that, what we could do is now we have this relationship. We can use this to find an. So an is the square root of the magnitude of acceleration squared minus at squared. So instead of finding curvature and all that, what I could do is instead, well, our acceleration vector is we take another derivative and we get cosine of t minus t sine of t sine of t plus t cosine of t 0. So just differentiated velocity. And then we just look at this magnitude squared. So if I'm doing the magnitude squared, I don't need to worry about the radical here. So I get cosine of t minus t sine of t squared plus sine of t plus t cosine of t squared. So we FOIL both of these out. We get a cosine squared of t minus 2 t cosine of t sine of t plus a t squared sine squared of t, and I'll write this one in the next row. It's plus sine squared of t plus 2t cosine of t sine of t plus a t squared cosine squared t. So those cross terms end up canceling, and then we have a cosine squared plus a sine squared, and a t squared sine squared plus a t squared cosine squared. So that just leaves us with a t squared plus 1. And we're almost done. So we have that our an is equal to the square root of the magnitude of acceleration squared, which is just our t squared plus 1, minus our a t squared, which was just t, remember? So this is just minus t squared. Oh, sorry, it was 1. It was not t squared. Let's get rid of that. So this is just minus 1. So that gives us the square root of t squared, which, because t is always positive, just gives us t. So that means we can write the acceleration as just 1, this at, plus t, n. So we can use the Pythagorean theorem to find an or at or the magnitude of a squared if we know 2 of the others. Okay, with that, I think